Okay, so thanks again for listening to these videos. This should be the last one for this moment on this buck converter series. And what we'll go to now is we saw that we compiled this block here. Now we'll go to another diagram set up. Okay, this diagram again, this one here will run at 100 Hertz because the JTAG interface has a limited bandwidth. We'll run it in real time so we can see the load steps in order, and we'll repeat the simulation. Whereas before we had this diagram, remember, and this one here is at the 100 kilohertz full rate. Okay, so we go to here. And what we can see is we're going to be set basically the poles and zeros to a base value based on the simulations we previously did. We've got target interface block here. This is simply put in by going to Piccolo target interface. Here it is here, the same one. It's the automatically generated from the code that we compiled in the previous diagram. This here is running at 100 kilohertz. Even though the diagram will run at 100 hertz, it will run at 100 kilohertz on the MCU. Okay, so all we need to do is connect to the target board, and we can do that right now. Run this up. Okay, what we can see is we'll switch this on. You see the soft start ramp up. At the moment we're not triggering anything, so we'll switch on the load and we'll start the trigger. And here we go. Here we've got the output voltage. Here we've got the load step. Here as we said, we had a 2 millisecond delay from the trigger of the output buffers. After 2 milliseconds we threw on the load at the 0.95 duty cycle, and after 6 milliseconds from the initial trigger we switch off the load, and we're triggering this continuously as we're doing it every second. So what we can do is we can have a look on the video on this as well. So if we switch this on, okay, we've got the LED blinking at 2 Hertz faster now because it's on. We can always switch this off. You can see here, we can switch it on again. It will soft start and ramp up, which we can see there. We can try the poles and zeros. Obviously we've got a fair bit of overshoot on the current here. We can put this down. We can make it very slow. We should see slow down the response significantly. We can see the step here. Okay, we can speed this up, and we certainly increase the response here. We still haven't got that much ringing, but if we try to go up too high, we're starting to get some oscillation in there. Okay, as you can see here, go up further, we'll get the buck converter starting to get a bit noisy. Okay, not yet, but okay, and we can do the same with the poles, and obviously the zeros as well if necessary, and find a best response on running as a hardware in loop on the actual hardware. Okay, so I hope this is informative. I hope it can help you to get more confidence in the use of this block set. the debugging features are very useful. They're very convenient. The programming, the compiling is very easy. Building blocks is very easy. Manipulating diagrams is extremely easy. Returning to diagrams after years without doing a diagram is very easy. To go into the block environment and just go in there, we can have thousands and thousands of blocks, and we can dig in and see what's happening immediately, basically from the block diagram environment. The code generation is reliable and very efficient, and I don't see that we could do much more with the design itself. It's such an easy process. Okay. Basically, all we need to do from this here now to generate a proper code, all we would need to do is tools, code gen. We can deselect this, select target flash. We can burn this to the flash of the microcontroller, and it will run independently in the microcontroller. No need to do anything else. This is a diagram. We've optimized coefficients. These last coefficients that were there will be there. We can set it up with a normal compensator here. For example, we can go to digital power code gen compensators 32-bit or FPU. We can do whatever you want there. 3-pole 3Z. We can take the one without pins, and we can set our coefficients here. We can bring them in from a file as we did before in the simulation, or we can directly enter the coefficients there. That will give us a bit more efficient calculation in there. We don't need to actively change the coefficients themselves. Okay. So, thank you for listening. I hope you liked the videos. Maybe we'll do. I would like to do some more as we add more features to the block set, and we more complicated control routines. We can do these at a later stage. Thank you. Bye.